Hello, Algebra 2. Today we're going to be looking at our first theme in the broad area of statistics and probability. And what we're going to do first is look at counting methods. So counting methods have to do with a branch of math called combinatorics. There are many different ways to count things. You can get a PhD in just one little subfield of counting, or combinatorics. What we're going to do today is look at three situations involving counting. And they'll involve some tools which are useful in advanced math as well. So the first one kind of comes straight up out of elementary school. I think you've seen this one before. Third graders and such are exposed to problems like this, usually at least. So that one is the fundamental counting principle. Fundamental standing for like fairly obvious, way back. So we're going to look at the theory behind these three counting techniques first, and then we'll look at a variety of problems and try to fit each problem to one or the other of them. So, fundamental counting principle. I defined it fairly similar to the way our textbook defines it this time. This morning we tried to define it nebulously and it didn't work out real well. So, I'm going to say the fundamental counting principle applies when you have C1 ways to choose item 1. So you've got one item, you've got a few different choices. Like color of marker, I have 4 choices. No, I only have 3 choices here. So C1 would be 3. C2 ways to count another item. So maybe I'm trying to figure out color of marker, and I'm also going to figure out how many ways I can write on a type of paper, and I've got 5 colors of paper, then C2 would be 5. And C3 ways to count a third item, and you just keep going until you run out of categories or types of items. If that's the case, then you can figure out how many possibilities there are combining all those different types of items very simply. Do you guys remember how to do that? Do something very simple. You take how many ways there were to count the first one, which in this case I called C1. I just gave it a random name, right? Like choice 1. That's why I called it C. And you multiply that by how many ways there are, or how many different choices there are for the second item. And you multiply that by the number of choices for that third item, and you just keep going with multiplication until you're done. And that's how many possibilities there end up being. So it'll be very clear once we get to some concrete examples. But right now we're going to focus more on the theory, because I think I jumped in too soon this morning. Okay? All right, 2 other ways to count. One is called permutation, one is called combination. These might be new, I don't know. They're almost identical techniques. So a permutation applies when you have a finite group of items that you're choosing from. You're selecting out of. So a lot of the time you'll see the word out of or selecting from. Those are all key words that this is either a combination or a permutation kind of situation. The most important part about a permutation, though, is this. That order matters. So we're going to talk a lot about order mattering and or order not being consequential today. A combination is the exact same situation. If you have one finite group of items, like a bag of 12 things, and you're selecting maybe 3 out of the bag at the same time. Except combination is slightly different in that, in this case, you don't care about order. So we'll come up with how to do the possibilities in a second here with the math. Before I did that, I wanted to think about a real simple situation and what a combination or permutation would be like. So I thought that a great motivating example would be thinking about choosing letters. Okay? So your choices are between the letters A, B, and C. So you have A for the first letter. The second letter, you could go BA or AB, right? And then for the third letter, when you put it on this combination, you could have a few different things. You could have what? BAC, ABC, where would that go? Maybe right here? Let me space this out just a bit more. So how could this look? We could have BAC, here we could have ABC. What else could we have? We could put that like C between the B and the A, couldn't you? Where else could you put it? C, A, B. I don't know if I chose the best way to do this. Dang it. A, B, C, what else could we have? CBA hasn't been done. What else? I think that would have made more sense here with my BA, wouldn't it? Not that this really matters, don't get too involved here, but I was trying to keep B and A as closely together as possible. BA, BA, and BA here just has the like C dropped in the middle. So here I've got A, B, C, and what else? I could drop the C first and maintain the A, B, or I could drop the C in the second spot, so it'd be A, C, B. You could take a second and make sure that those are all unique possibilities, but I think they are, right? So, what am I using this to motivate? The idea here was, how many possibilities are there? So, when we started here with just one letter, there was only one possibility. How many possibilities when we just went to two letters? 2. How many possibilities here? 6, but see, I'm not going to write this as 6. I'm going to write it a special way. I'm going to say, really, 2 is 2 times 1, right? Here, think about the number of branches on each branch. There's 3. How many of the different kinds of branches were there? 2, and those all go back to 1 character each. 1. If you go to the next thing, rather than trying to find the pattern from 1, 2, 6, you could go, what? 4 times 3 times 2 times 1. In other words, there'd be 4 branches coming off each one of these, and that would lead to this kind of situation. So this kind of thing over here in red, I'm just going to erase my tree diagram. We're going to be using trees to keep track of counting in all kinds of different ways. This kind of red over here has a special mathematical operation to it. So for instance, this is called 3 factorial. Little exclamation point doesn't mean 3. It means 3 factorial. This is, in other words, 4 factorial. And each one of those, did order matter or did it not when we were trying to think about the different ways A, B, and C could be placed? Order totally mattered, right? So when order matters, which one of the things are we working with? Second one, permutations. That's where order matters. If order didn't matter and we were just thinking about how many possibilities there were using the characters A, B, and C, how many choices, how many possibilities would there be? 1. That's exactly right, because all of those things, whether we had BAC, BCA, or any of those other possibilities, are exactly the same because they use the same 3 characters. So there's only one combination, but there were 6 permutations of the characters A, B, and C. Okay, so I'm going to write down how to do the math on this with an example on each one, not with like a special thing. So let's think about another common motivating example. Let's think about selecting a group of, I don't know, should we say, selecting 2 people out of, there's a key that it's one or the other of these, right? Out of a group of 5. So we've got 5 people to choose from, and we're picking 2. So what do you guys think? Does order matter there or not? I think it kind of depends. Probably not, unless I say, well, maybe these people have special roles to fill. So if I'm choosing one of them to be my best friend, and one of them to be my kind of friend, then whether I choose Kevin, if he gets chosen as one of the 2, it matters whether he's in the best friend slot or the he's kind of my friend slot, doesn't it? I think that those are 2 unique, different things. So in that case, order would matter. So let's say on top of this that we're choosing a best bud, and kind of friend isn't very nice. What would be another way to say that?
Wait.
Okay.
Kind of friend.
I like it. Had to test my spelling though, Kaylee. I don't know if that's spelled right, but I don't care. So I think this time order matters. So we're going to be doing a permutation. So the one we're going to do is 5 permute 2. So let's think about how that goes, and let's think about back to our character choices with A, B, and C. So how many things are we choosing? We're really just choosing 2 positions. How many choices are there for the first position?
5.
So let me write this out real clear here. So you know what? First person, let's say best bud. There's 5 choices for that, right? And we're going to be multiplying just like we did before. And then we've got the acquaintance, or the second person. How many choices are left? Because we already had to choose someone here. 4. Do we want to keep multiplying, or are we done at that point? I think we're done because we're only picking 2, right? So the answer here is 20. It's not all of 5 factorial, or 5 times 4 times 3 times 2 times 1. It's just 5 times 4. That's the answer. So that's 5 permute 2. The thing is, a lot of the time we don't want to do it that way. So we're going to use factorials to help us. So what's a formula that we can use to get this same answer that'll work in all situations? Okay, that's what you're going to want to be doing these with. So how do we get 5 times 4? Well, let's be creative here. How can we use factorials to get that? I'll give you a hint. Make it a ratio. And up on top, we're going to want 5 times 4. What would the rest of it be if it's a factorial, though? Except we don't want that 3 times 2 times 1 in there, right? That's not part of the answer. So how can we get rid of it? We could divide by it, right? And then that would totally cancel out. So really, what does this become? It's really 5 factorial over what? What's this down here? It's 6, but I need it as a generic expression. It's 3 factorial. So how do you get 3 factorial from just thinking about the 5 and from just thinking about the 2? You go 5 minus 2 factorial. So that's kind of thinking backwards. What we're going to do from now on is we're going to say, if I have 5 permute 2, or if I have a group of 5, order matters, and I'm picking 2 out of that group, I'm going to do it as, put this in red, I'm going to go the first number, the size of the group on top, factorial, over the difference between these, 5 minus 2 factorial on the bottom. And my next step will be to go, that's 5 factorial. And here's really 3 factorial. You can write out an extra step or just use common sense and say that's 3 factorial. Chop, the answer is 20. That's how permutations work. So let's think about that exact same situation, except now, instead of choosing a best bud and an acquaintance out of those 5 people, we just want to pick 2 friends. So I'm going to say only 2 friends. If we're only picking 2 friends, I don't think order really matters anymore. So if we're only picking 2 friends, you guys tell me, and this is maybe the little bit of a tricky part when you're starting out. Are we going to have more possibilities, or are we going to have less possibilities? It's less. There will be less possibilities, because in that first situation, I could switch best bud and acquaintance and get more possibilities. In this situation, I'm just like, well, I picked Kevin and I picked Daniel, so that's it. Doesn't matter if I switch their places, they're still the same people, right? So in this case, I think we're going to have less possibilities. So how does it work? I think you do that same thing. You go 5 factorial, and I'm not going to be as theoretical with this one. You still go 5 minus 2 factorial. This is going to be what it is to be 5 choose 2, though. So, combination, 5 choose 2. 5 factorial over 5 minus 2 factorial. Except I need there to be less possibilities now. So where does that less come from. I'm not going to dig into the theory on that as much as we did with the others. Be interesting to try though. You need to divide by something else as well. Think about it. In fact, we can dig into the theory. I made this example simple enough. How much do we need to divide by? I hear a couple people saying it. What's the answer going to be? If there were 20 ways to pick those 2 slots where you could flip-flop them, you just got to take the flip-flop out. So you got to take 20 and do what? Cut it in half. That's it. So, cut 20 in half and you get 10. How am I going to make this come out to 10? I'm going to add, and I should have made this in red, my bad. It's not my day today. We need an extra 2 here, but I don't think 2 is going to be the thing for every situation, is it? Think about where that 2 might come from. It came from this 2. So instead of just saying 2, I'm going to say 2 factorial, because this was the 3. I wouldn't want to be dividing by 2. I'd have to divide by 6. Okay? So, if you're doing a combination, you divide with an extra thing right here. And that takes you from more possibilities to less. So you might want to write that in your notes. Combinations have less possibilities. Permutations have more possibilities. Just the way that the words are phrased here can sometimes be slightly confusing. Just takes experience though. So let's look at a variety of examples where we have to choose one of these counting techniques to figure out how many possibilities there are. Okay, so now students, let's apply those counting methods and select a method and then figure out how many possibilities there are for each. So I kind of left off the question on each one. It should be pretty obvious, like how many different arrangements or how many possibilities or whatever. That's what we're doing. Okay, so number 1. You guys tell me, do we think this is fundamental counting principle? Do we think it's permutation? Do we think it's combinations? So you're making an English trifle. This is inspired by an episode of Friends. You have 4 choices of meat. Hamburger, bacon, steak, chicken, I don't know. You have 3 choices of custard. Vanilla, chocolate, raspberry, I don't know. And you have 5 choices of vegetable. Peas, onions, carrots, etc. Obviously something went wrong with this recipe. But you don't know that because you're Rachel. Okay? So you don't know that something went wrong with this recipe, and you're just going to choose one of each of these things. Do we think this is choosing out of one bag, or do we think that there's like different kinds of items and we're going to have to multiply the possibilities? I think it's pretty obvious there's not just one great big bag, especially if you put all these things in a bag, you're going to have a problem. Yeah? So, this is fundamental counting principle. So how many possibilities are there? Multiply and you're done. In your practice, you're going to see that the book does group them a little bit. It'll say like these are fundamental counting, these are permutations. I would try to ignore the book's organization and treat each one as unique, because that's the way my quiz or test will be. And that's the way like any real situation is, right? You got to know which counting method to apply. So this one's super easy. You're going to go, oh, there's 4 of these, there's 3 of those, there's 5 of those. Multiply and I'm done. I'm going to go 20 times 3 because that's easier for me to do. So it looks like there's 60 trifle possibilities, all of them equally disgusting. Okay, there you go. So make sure you put units or some indication of what you just did on, just like usual. Okay, second problem. Your clothing store, I don't know, you're opening a new fashion shop. Your shop has 7 jackets. You wish to display 3 in the window. How many ways can you do that? So, do we think this is fundamental counting principle, or do we have like a group of things we're choosing out of or from? So it's a group of things. It's a group of jackets in this case, right? So that we've just had to decide first, well, what do we have to decide first? Does order matter, or does it not? Kind of a judgment call in this situation. So what do you guys think? Is it going to matter if once we have 3 jackets, if we have like 1 here, 1 here, 1 here? Like which arrangement we have? It's kind of a judgment call. I think you could do this one either way. We probably need some more information. I'm going to say that yes, order does matter. In other words, there's going to be more possibilities because maybe I want to put the jacket I think will sell the most right in the middle. You know what I mean? So that's what I'm going to say. Benefit of more information, we're not sure. So I'm going to say I think order matters here. As soon as you choose that, I'd encourage you to think, are you going to have more or less possibilities because of that? It's going to be more, because not only are you choosing 3 jackets, you've got different ways to arrange them. So as soon as you know that order matters, or that you're going to have more possibilities, how many possibilities are there? So possibilities, you can write that however you like. Is it permutation or combination? You can use your notes if you need them. Permutation. Permutations are always bigger. So group of 7, so it's 7 permutations of 3 jackets at a time. So let me do that as we go. 7 factorial over 7 minus 3 factorial, which is 7 factorial over 4 factorial. And there's nice ways to simplify factorials. For instance, you can stop it wherever you want. You could go 7 times 6 factorial. I don't want to stop yet, though. I go 7 times 6 times 5 factorial, but I don't want to stop yet. Or I go 7 times 6 times 5 times 4 factorial. I think I'm going to stop there. Why did I stop there? Because now I can get rid of these entire factorial quantities. And then I'll have my answer of 7 times 6 times 5. I might need some help. 200 plus 10, 210. There's 210 ways to arrange those jackets in my storefront, so I better get thinking about what I want to do. Okay? There you go. I don't think a clothing store person would do that. Kind of a...
Because one complements the other, one's in the center, so...
You want to see which one you think's best.
Okay, here's another one, inspired by current political events. I think this is how Donald Trump makes decisions sometimes. If you're out there, Mr. President, I'm sorry. I have faith in you. But this is what the evidence indicates to me at this point. So he has 5 cabinet positions open. I think there's more than 5 cabinet positions, right? Like Secretary of the Interior, Secretary of Defense, etc. So he has 5 vacant positions. I wonder why. Leave that to you. He has 12 candidates for the jobs. He's going to interview all these jobs at the same time. It's like when Ben Carson didn't get Secretary of Education like he was thinking he would get. He got something else instead. Anyway, so that's the situation. We're going to see how many possible ways these jobs could end up coming out, right? How many different ways could the president decide to do this? So what do you guys think? Does order matter here or not?
Well, since you don't have the positions, like everything that
Is it going to matter who gets what job?
Yes.
I think a lot.
well, for a degree, yes. For this problem, no.
Order matters. Whether I'm the Secretary of Defense or the Secretary of Public Housing, it's going to be kind of different jobs, right? Yeah, I think so. So I think order matters. So permutation or combination? Permutation. So that's what you should be thinking. Permutation. Then you should be thinking lots or less. Lots. So we'll say more possibilities, and then you do the math. So you say, how many are in my bag? How you fit people in a bag, but people are in a bag. So there's 12 of them, and how many am I picking at one time? Of course, I'm picking 5. So if you're watching the video, it'd be a good idea to pause it. For today's sake, I'm going to just do this. So we're going to have 12 factorial over what factorial? Skip a step. Not over 5 factorial, but over 7 factorial. And now you can skip a step here if you want as well. I'm going to rewrite the 12 factorial as 12 times 11 times 10 times blah 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 times 7 factorial, so it'll cancel. So all that will be left is 12 times 11 times 10 times 9, still kind of a lot, times 8. 7 factorial here will cancel with the bottom, so all I've got to do is that. You guys use your calculator and tell me on this one.
5,040.
That?
Yep.
Okay, so that's a lot of possibilities.
And random number generators.
Okay, another one.
There was a blind one.
Here's a pretty standard one. I know you guys have some like this in your assignment. Pretty important, I think. So you're building a password from 5 numbers, 3 letters, excluding X, we don't want to use X, and 2 characters. I don't know how many characters there are. Do any of you guys know by chance exactly how many characters are on a keyboard?
I can count.
I mean, we know how many numbers there are. We know how many number keys there are, right? How many?
10.
There's 10. 0 through 9. There's no button for 10, but 0 counts as an extra one, right? Okay. How many letters are there? I think you should know that.
26.
26, but...
I like 5.
So there's only 25 there. Characters, I'm not really sure. It's somewhere between 20 and 30, I think. I don't know. I'm going to guess. I'll say 25.
Yeah, why can't we have X?
So that's like the money symbol, dot, dash, question mark, all the different characters. I don't know how many there are, so I'm not sure about this. But is this going to be a permutation, a combination, or a fundamental counting principle problem?
Combination, because it doesn't say it has to be in a certain order. You could have all 5 numbers and all letters. And then
True. I don't know if order matters, or does it? I think it matters. The order of a password matters. If your password is cat, that's different than tack.
Okay, well, I'm just telling you, if we're making a thing out of this, I'm not going to remember it. No one makes a password over random letters and numbers.
Yes, they do. I do. Anyone who's smart and understands things about crypto security does, Kaylee. So, my brother's a software engineer. You should see his passwords. Why? Because he can break other people's. So, yeah.
Well, do you
What's
know
up?
your password
So I
is
can't-
X excluded? Yeah, I don't.
So my password's
Because they don't want to use that.
I just said I don't want to use X because
Exactly.
I'm a PG
He's
kind of guy.
discriminating against
Okay?
X.
Do you forget your passwords?
All right, so I don't think there's not one bag we're drawing out of. It's a fundamental counting principle problem. We're picking how many digits? 5. So there's 10 of those. 10 choices, 5 times. And then I'm picking how many letters? 3. Each one has 25 choices. So it's kind of like I'm thinking about a password with all the different slots it could have, right? But this is fundamental counting principle, that's all it is. It's an elementary school problem, just a tough one. And then the last thing, I claim that there's 25 characters as well. You know what, let's pretend that's something else that's going to be confusing. Let's say, I don't know, there's 31 characters. Choosing 2 of those. So there you go, that's how long your password has to be. We're going to say that the first 5 are numbers, then the letters, then the characters. Otherwise this gets more complicated and we just don't want to go there today, I don't think. So when my class entered the computation a second ago, someone had a calculator error. So I just wanted to make sure that computation was good. So let's put it in our calculator. So how many passwords are there going to be? So we're going to have 10 to the 5th power. I'm going to shortcut 10 times 10 times 10 as 10 to the 5th. And then I'm going to have 25 because we had 25 letters to choose from. And we were going to pick 3 of those, so 25 to the 3rd. And we were going to go with our pretend number of characters, which I'm not sure about. We're going to say there are 2 of those, so 31 squared. So what does that come out to be? You can, of course, see the scientific notation right here. And so what is that? So this is going to be 1.5, and I'm just going to say approximately because once we get to this many possibilities, approximately might be good enough unless you're like a Star Trek computer or something, if you're data. So 1.50, I'm just going to round this to 2 times 10 to the 12th. Of course, that 10 to the 12th is trillion. We're on the order of tera possibilities now. So, oh my gosh, there's a lot of possibilities there. For a computer, maybe that's a lot, maybe that's not a lot of possibilities to crack. It all depends on what you know about cryptography. Okay, last example. So, this time you're a lizard connoisseur. I'm sure I spelled that wrong. French is not my language for spelling correctly. So that means, of course, that you really like lizards. You know what you're talking about with lizards. For some reason, That's what you are, I don't know. The pet store has 10. The pet store got a new shipment of lizards in. They have 10 different kinds. And you're going to buy 3 that you've decided. So the question is, do you think order matters here or not?
Yes.
Different colors.
I don't think so. I mean, it doesn't matter if they're different colors. Well, we'll get to it. Let's think about this on a simple level first. We're just picking 3 lizards.
Don't listen to me.
I don't think order matters. You get 3 lizards, they're the 3 lizards you have, right? So, if order doesn't matter, does that mean we're going to have more or less possible? I think we're going to have less. Because we don't want to count like the green lizard, the blue lizard, and the red lizard as separate from the blue lizard, the red lizard, and the green lizard. They're still the blue, the red, and the green lizard. Or you could go, you want me to name some lizards? Still different than the monitor lizard, the Komodo dragon, and the, I don't know, striped lizard from around here. Okay?
The order you just buy it.
So, combination or permutation? Combination. What specifically? 10 to pick from? Choose 3, and you say that as choose, not combo 3. You could say combo 3, though. People know what you're talking about. So then you go, okay, that's 10 factorial over 10 minus 3 factorial, which will give us 7 factorial. That's permutation, the way you divide out the choices that are duplicates. So you avoid counting them twice, is you divide by that as well. So that means we're going to have 10 factorial, 3 factorial, 7 factorial. So if you're doing this by hand, which I encourage you to do all of your problems like, but I'll show you how to do it with your calculator too. I'm going to go 10 times 9 times 8 times 7 times 6, or should I have stopped before that?
Where's the 3 times?
I think I should stop right here. I mean, it's up to you, but I'm stopping right there so I can get rid of these pieces. Have this left, and then 3 factorial I can just write out as well, right? And you can play with the numbers however you like. The other day I started to do this with you. I started to break things down as factors. Well, here's one of the reasons I did it. So 9 over 3 simplifies to 3, right? You can go 8 over 2 or 10 over 2, however you like it. I'm going to go 10 over 2 simplifies to 5, right? And then I've got 8 and 1 left, so I've just got 8 left. So I think that that is 3 times 40, which is 120. So there's apparently 120 ways I can select 3 lizards out of this group of 10. Did you guys get the same? Now notice, was there any rhyme or reason about how I did this? No, I tried to pick the easiest way. Let's check it with our calculator just in case I chose a way that was incorrect. As I did this morning. It's a couple things. And nobody caught me. Shocking. So, if you go to the math menu, there's something with probability, and I think that's kind of what we're doing. Stuff.
Do 3, not 2.
There's the factorial button if you need that, so you could do it long ways, right? So you could go, okay, pretty sure I know choose is, and go alpha y equals, and go 10 math factorial over, okay, 3 math, still a long way to do it, times 7 math. Looks like I did my math right there, but maybe I was just confused about how combinations actually work, right? Like I was this morning on a couple. So I'm going to go math, probability. You guys see combinations anywhere? This is number 3. You can click that first. If you do, you're going to have to go back and just like backtrack. What was n? What was our size of our bag? It was 10. See, if you do that, it kind of deletes it. Some calculators it does, some it doesn't. Mine does. So I have to hit 10 first and then go hit choose. But anyway, you just got to get it to where you can do 10, choose 3. And there's the answer. So when you're doing your assignment, in my class at least, I want to see all the work on all these problems in the first assignment. You're welcome to check it with your calculator. Because on the quiz or test, I'm going to want you to show it. You need to work with factorials to get good mathematics. Okay. So there you go. Hope you found that helpful.